In 1927, Werner Heisenberg discovered what is now known as the uncertainty principle. It is a principle at that time and even today mainly applied to very light particles, or at least obvious for very light particles like electrons or other atomic or subatomic particles. What it says is that the more precisely the position is determined, the less precisely the momentum is known in this instant, and vice versa. Now, the origin is probably quite mathematical. Heisenberg has a way to explain this physically, and we imagine, say, there is an electron. Say electron here. Now, and suppose that we can't see the electron at first, but we want to try and measure or determine its position, where exactly it is. So, since it's such a tiny particle, you might imagine that I would have to use an extremely powerful microscope. Right, so I'm just going to draw a lens here to represent a microscope, and then I must shine a light, maybe of a very short wavelength, and try very hard to focus on this tiny electron. Okay, so when light falls on this electron and gets reflected, then I can see it, right? I will be able to see the tiny electron, just like what we might try when we want to look at the bacteria under the microscope. The only trouble is electrons are much lighter than the tiniest bacteria. They are so light, in fact, that when a photon of light hits the electron, right, imagine from what we understand of the photoelectric effect from Einstein, that light is quantized. Light happens in particles called photons. And when a photon hits the electron, the electron would bounce off. So the moment, that means that the moment I try to look at it with a microscope, I need light. We need light, of course, to look at it. Right? The moment we try to switch on the light and look at the electron, when the light falls on the electron gets bounced away by the light, by the photon of the light. So although light would still be reflected, and you would still see and find out the position of the electron, the very act of making this observation, the very act of just looking at the electron, means that we have disturbed the position of the electron. So immediately after we have looked and found out where the electron is gone somewhere else. Okay, so that means that the moment we have precisely determined the position, the moment we have done that, the momentum would have changed. The momentum would just have changed completely, and we would have no idea what this new position is. So that is a kind of physical picture that Heisenberg proposed after he derived this uncertainty principle in a possibly more mathematical way to explain the physics of electrons and atoms at that time. Now, of course, it's a general principle that we now know apply to all particles, big and small, right? Except that, as I've said, it would probably be more obvious for very light particles, or more easily observed, maybe. Okay. Now, there are different ways to actually understand the reason for this uncertainty principle and how it is derived. Now, let me first start by writing out the formula that Heisenberg derived for this principle. Yes, there is actually a formula. Now, let me start by writing down some symbol. Okay, we need some mathematical symbol. So let's say that this is the x direction. Okay, let's say we just consider the simple case that the electron is moving along a line, so its position is given by x, and its momentum is given by p. So the formula for the principle is that the uncertainty in x times the uncertainty in p. By uncertainty, we might also think of it as perhaps the error in measurements, but error in measurements depends on the kind of instrument that you use and so on, which can have very big errors if it's not good. So we use the word uncertainty. When we use the word uncertainty here, you can think of it as maybe the smallest possible error, if you like, that is inherent in this physical system. That means the error that you would still get if you have a perfect instrument, right? That's the idea here. These are the uncertainty. It doesn't come from the instrument. Uncertainties that comes from the very nature of the particles themselves. So these are the uncertainties in the position and the uncertainty in the momentum. So the relation says that when you multiply those two uncertainties together, the answer would be about roughly equal to h, the Planck's constant. Now, just if you recall what the Planck's constant is, h is a very small number. It's 6.6. Let's see, 6.63, I think, times 10 to the power of minus 34 joule second. Right. So this is the formula for the uncertainty principle. Now there are many there are a number of different versions of this. You might also see versions that say this is equal to h bar over 2, and which defines this as the root mean square values of x and p. Okay, and versions that includes a more than or equal sign. Okay, so that it can be made a lot more precise. With the more than sign probably intended to include measurement errors from instruments. Right. But for this and maybe the next video, I shall stick to this form because I mainly want to explore, to try to understand the physical ideas behind this, and then to use this relation to perhaps make an estimate of the kind of energies that the particle would have, say in atoms or other systems. So I mainly want to consider the uncertainties due to the nature of the particles itself.